and then came to Stanford as a graduate student about a decade ago, and joined the SITP, where she got her degree. She subsequently went as a postdoc to Perimeter Institute and to New York University. And as of this academic year, she's a professor of physics at the University of Washington. Masha is one of the rising stars of particle phenomenology. She has done outstanding work, both in looking for new physics through astrophysical phenomena and in searching for new physics through small-scale experiments. Today, she will talk to us about how to look for new particles in the sky.
All right, thank you. It's really great to be back in my academic home. Thank you for the introduction. So today, I will tell you about a new direction of looking for new light particles in around astrophysical black holes. If I can switch my slides. Good. So we live, for better or worse, in the age of the standard model, where we have figured out the minimal set of particles and interactions that largely describe the microphysics of our universe. This standard model, developed over hard work over many decades, has had great successes, including most in the last decade, the discovery of the Higgs boson, which completes the model of electroweak symmetry breaking and masses in the standard model, and the excellent agreement between experiment and theory, which is going to greater and greater precision, pushing 12 decimal places in agreement in some experiments. But of course, we know this is not the whole story. We know that all of these particles and interactions make up only a very small component of the energy density that we see out there in our universe. And we also have a lot of theoretical questions that are left unanswered. For example, why does the Higgs not seem to receive the quantum corrections from high scales that we expect in the quantum field theory? Similarly, why is the electric dipole moment of the neutron so much smaller than our calculations? And more generally, can we say something about physics beyond the scales that we can access directly? How can we start filling in our understanding of these 16 orders of magnitude between what we've probed at colliders and where we know something interesting should happen to the theory of gravity? So today I'll focus on ultralight particles, which are motivated by two of these questions. The first is a theoretical one, as I mentioned, the puzzle of the smallness of the neutron electric dipole moment. And the second is the experimental observation of dark matter, that we need a new particle or particles in our theory to fully describe the phenomena that we observe out there in the universe. So these two questions point us to potentially new light particles that we'll try to look for out there in the sky. So first, I'll spend a bit more time motivating these ultralight particles, and then I'll talk about a very exciting phenomena where you can use astrophysical rotating black holes as laboratories for these new light particles. You can form huge amounts of these particles in bound states around black holes. Once we form these bound states, we'll see in the last part of the talk how we can try to observe them through various processes of their emitting different types of radiation. And we detect these in the lab. So to start, what is the strong CP problem? Probably, okay, there's something here. Hold on. All right, sorry about that. So it's the statement that in the standard model, there are already large violations of these types of discrete symmetries, which we call charge and parity. Parity is an easy one to understand. It's flipping all the spatial directions to their negative. And given that there's already large violations of the symmetry, for example, in the quark sector masses, we expect the strong interactions to significantly violate the symmetry as well. And we can see that in the example of parity, if parity is violated, then this would allow the neutron to have a dipole moment, an electric dipole moment. So what's that? So we have this neutron here. We know the neutron has a spin, which is a magnetic dipole moment. It causes it to have energy and split energy states in a magnetic field. But it also is some composite object which could have a dipole moment, electric dipole moment. And under a parity transformation, the electric dipole moment, which scales as radius, will flip sign, whereas the pseudo vector, which is magnetic dipole moment, will preserve its direction, which means that, for example, if they started out in the same direction, they will end up in opposite directions. And this clearly is not consistent with a parity symmetry. So if we see, as we expect, a non-zero electric dipole moment for the neutron, we would know that parity is violated in the system. And the parameter by which it's violated is called theta in the strong interactions. And if you just compute what this is, the estimate is that it's roughly given by the size of the neutron times the charge of its constituents with some extra loop factors. The actual calculation is a bit more complex, but that gives you the right order of magnitude. And so this is our expectation. If the violation is order 1, like it is in the weak sector, then this is the number we would expect. But the experimental upper bound is about 10 orders of magnitude below that value. And this is what's called the strong CP problem. If theta is a fixed parameter in our world, in our theory, this is a huge unexplained tuning in the problem, in our understanding of the standard model. Fortunately for us, there's been an elegant solution that's been around since the late 70s, which is, let's say that theta is not a fixed parameter in our problem, but it's a dynamical field. So now theta is some scalar field A normalized to a high symmetry breaking scale F. And this field has a potential that it gets from the strong interactions. And the minimum of that potential sits at the CP conserving value of theta of 0. So without introducing this new field, which we call the axion, the expected CP violation will be some order 1 value in this potential. But being a dynamical field, it wants to relax to the minimum of the potential, and that gets rid of the presence of CP violation in this sector. And I also want to say, if people have questions throughout the talk, please ask, as well as at the end. It's more fun to stay on the same page with the audience. So this motivates this new light particle, the axion. As I said, it's a solution to this theoretical puzzle of small numbers of why is this measured value so much smaller than what we predict. And it predicts this new light particle, which has a mass that's much, much lighter than any particles that we already have observed. And it's inversely proportional to this high scale F that sets all of the interactions that this particle has with itself and with standard model. In addition, after this particle was proposed, people realized that it's an excellent candidate for the dark matter of the universe. It's cosmologically stable, although on very long time scale, it can decay to 2 photons, but that time scale is much longer than the age of the universe. And also, they tend to pop up in a lot of extensions of the standard model, like string theory, where you have extra dimensions, and these axions correspond to fields living in the extra dimensions that remain light at low energies. So we're all of these properties are true for the QCD axion, the particle that solves the strong CP problem that I started with. But the last 2 points are kind of interesting in themselves and are true for more general types of particles. So not necessarily the QCD axion, but other axion-like, what we say axion-like particles, or also spin 1 particles like the dark photon. They can also be stable, weakly interacting dark matter candidates that are produced in the early universe. And they're often found in UV completions of the standard model when we try to extend it to high energies. So these last 2 points are interesting enough that we want to generalize this QCD axion solution, which has this one-dimensional parameter space, to a broader set of ultralight particles. And this, the parameter space looks like this. We have, on the left-hand side, we have the parameter space for axions. On the right-hand side, we have the parameter space for dark photons. So the x-axis is the mass in electron volts, and the y-axis is the strength of the interaction of these particles. The green line here is this QCD axion I talked about, which solves the strong CP puzzle. The blue regions are kind of the simplest places where you get dark matter from a period of early inflation in the early universe for generic axions or axion-like particles or dark photons. So this region was pointed out by Peter Graham and others here, that you can generate dark photon, dark matter just by the assumption that you have a period of high scale inflation in the early universe. And the gray regions are already searches or exclusions that have been placed on these particles through various methods. And you might notice that a lot of these gray regions are dominated by astrophysical objects. So here we have exclusion through stars. Here we have supernova 1987A. And so that tells you that one of the better ways to look for these ultralight, very weakly coupled particles is by looking at large, dense objects in the sky. And this is easy to understand. For example, if you have the sun, we have our photons that get emitted from any point inside of the sun, and that emission is very efficient. We produce many, many photons in every little volume element of the sun. An axion or a dark photon is going to be much, much more weakly interacting. So if you're much less likely to emit it in any given point in the sun. However, that also helps us because once you emit it, it's going to escape without hitting any other particles on the way. It's just very unlikely to interact. Whereas the photon is going to rescatter many times and take forever to actually get out and change and cause some change in the emission from the sun. So this means that even though these particles are much, much more weakly interacting than anything that we deal with on a regular basis, like photons, they can actually carry away a reasonable amount of energy density because they can carry away energy from any point in the volume of the sun, whereas photons effectively are only carrying away energy from the surface. And the other thing that helps is that these are very hot objects, and these axions are typically interact what we call higher dimension operators. So that means that the strength of the coupling is less weak when we go to higher energy scales. This is a familiar comparison in the history of weak particle physics. So for example, the same thing happens with a neutrino. It's also weakly interacting by the actual definition of weak interactions, and it can be produced anywhere in the sun and carry away a lot of energy. There's different processes that produce these two particles, but even though neutrinos are so much more weakly interacting, we normally don't think about interacting with them on a day-to-day basis. They still carry away about 3% of the energy flux of the sun. So, and the sun has been one of the places where we've really learned a lot about the interactions of these very, very weakly coupled neutrinos. So you can expect that this is also one of the places where we can learn about even more weakly interacting particles like axions and dark photons. Going to even more dense and exciting objects, we can go to a young hot neutron star. So if you have, say, a neutrino in a very dense core of a neutron star or recent supernova explosion, even a neutrino will take some time to get out. Whereas a more weakly interacting particle, like these axions or dark photons, can stream out freely. And comparing these two processes will again give us some of the better constraints that we have on the strengths of the interactions of these types of particles. So those are putting into context those gray regions on the parameter space plots that I showed. But if you recall, there's still a lot of interesting empty space, and we want to ask the question, how do we learn more about this parameter space? Can we think of new ways to try to probe even more weakly interacting particles than what we've achieved so far? And the natural progression here is to go from to more and more dense and compact objects, which is a black hole. So that is not exactly a good analogy, because previously we were using the thermal energy of the sun or of the neutron star to produce these particles, and looking at how they carry away energy and comparing that to standard model processes. Of course, if you produce, you can't produce something inside of a black hole and hope to observe it. But I'll tell you about another mechanism, which is called black hole superradiance, where you can, instead of extracting the thermal energy of the object, you can extract the rotational energy of a real astrophysical black hole and place it into bound clouds of these ultralight particles. And then these will have observable consequences that we can look for. So before going into the story of black holes, I want to demystify the process of superradiance. So it's quite a general process kinematically, where you can extract rotational energy of any kinds of lossy rotating object. So it doesn't have necessarily anything to do with the fact that black holes are these exotic objects, but it just has to do with the fact that it's rotating and it has dissipation. So let's see how that works. Let's take a cylinder like this. Let's say it has a very frictionful surface, so that when you try to scatter something off of it, like a ball, it'll slow down as it impinges on the cylinder. Now, if instead the cylinder is rapidly rotating, as the ball comes in, it'll actually get thrown forward with more kinetic energy than what it came in with. This is perhaps counterintuitive, that losses can lead to increase in energy, but if the cylinder is rotating much faster than the tangential velocity of the ball, then the losses will actually act to increase the forward velocity of the object. And the same thing happens with waves. If you have a wave that scatters off a rotating object, it will increase in amplitude as it scatters if the angular velocity of the rotating object is fast compared to the angular velocity of the wave. Now here the energy extraction is a little different. Instead of increasing the kinetic energy, you are going to stay in the same with the same energy and momentum, but increase the number of particles in the wave packet. So, and the growth will be proportional to the incident amplitude of the wave, and it's also proportional to how efficient the dissipation is at the surface of your rotating object. In this case, we're going to be talking about black holes. So our object is really perfectly dissipating because anything that impinges on the horizon will get absorbed. And if it's spinning fast enough, if the black hole is spinning fast enough compared to the phase velocity of the wave, so its energy divided by its angular wave number, then the wave will get amplified. So for example, let's look at what happens if you have a rotating black hole with an incoming gravitational wave. So this is a full numerical general relativistic simulation that was done where you have a blue gravitational wave with some angular momentum that's impinging on this rotating black hole at the center, and you can see it re-radiates a much larger amplitude wave due to the superradiance process where you slow down the rotation of the black hole and place that angular momentum into building up the amplitude of the outgoing wave. So this is very exciting. This is what, part of what happens in the gravitational wave dynamics when you have black holes merging, but it's not really that interesting in the grand scale of things, because you start with some wave and maybe you increase its amplitude by a factor of 2, and then it goes off on its merry way. What becomes more exciting is if this wave has a small mass, because then instead of having only unbound states of these waves, you can have bound states. Just through simple gravity, you have a gravitational potential that's noted here, suggestively by these blue lines. If you have a particle with some mass mu and some black hole with radius r, then if these wavelength of the particle is comparable to the size of the black hole, you can form bound states around the black hole that live outside of the black hole but are still close to it, so they can efficiently extract the black hole's energy. And the fact that these bound states existed and that they could extract energy efficiently was known in general relativity since the 80s. Basically, it's an instability of rotating black holes to light massive fields. But it was realized more recently by some people here that you might know at Stanford, that this instability can actually be used to look for new particles. So it's not just process that happens in GR, but it can happen in the real Milky Way black holes if we have a new light particle whose wavelength approximately matches the size of these black holes. So what do these bound states look like? Let's get a bit more intuition for these types of states. So we have just a particle with a mass mu. So far, we're not assuming anything about its interactions to the standard model. This is all gravitational. So we have a gravitational potential far away from the black hole. It's a 1/r potential. And you have a proportional to the mass of the black hole and the mass of the particle mu. And we know how to solve a 1/r potential. That's the same as the potential of a hydrogen atom. And you can label the solutions in the same way by the principal and orbital quantum numbers. If you have a non-zero total angular momentum, these states are unstable to superradiance, so they can satisfy the superradiance condition and grow by extracting the black hole angular momentum. The big difference is that you can have a you can have an interesting boundary condition at the black hole location. So previously, if you solve your hydrogen atom problem, you impose that the solution is regular at 0 and at infinity, and you have everything that's nice and Hermitian. But here, the key thing is that the black hole is an absorber. That's what gives you this dissipation. And so that gives you a non-Hermitian condition where you can have a small imaginary pipe of your energy. So just like in hydrogen, you have the energy is the mass of the particle instead of the mass of the electron. Now you'll have the mass of, say, the axion. You have some binding energy where alpha is the fine structure constant, which is the gravitational fine structure constant. That's defined here as just the coefficient of the 1/r potential. And then you have this imaginary piece, which is positive or negative, depending on whether the superradiance condition is satisfied. So if the black hole is spinning fast enough, then this imaginary piece will lead to exponential growth of the number of particles in these bound states. So let's look at how this works in time. So on the left, I'm showing the parameter space of a black hole mass and spin on the y-axis, where 0 is a non-rotating Schwarzschild black hole and 1 is a very maximally rotating black hole. And then the x-axis is the black hole mass and solar masses. And on the right-hand side is going to be the number of axions that grow in this bound state over time. So let's say we have a light axion in the theory. It doesn't have to be physically in the vicinity of the black hole. So now we're no longer scattering in states from infinity, but we have some even quantum fluctuations of the field where you can have a 1/2 h-bar omega axions starting off in this level. And you have a black hole that's rapidly spinning. For example, let's say we had a merger like one of the ones you see at LIGO, and it formed a roughly 40 solar mass black hole with a high spin. What happens? In about 1 year, you build up this state where you populate many, many particles in this exponential growth process here. So you get as many as 10 to the 78 axions, all living in this huge coherent state. And the black hole drops down to the bottom of this blue region. So what are these blue regions? They're where you have these bound states labeled by angular momentum L equals 1, 2, and 3. And the black hole spin is fast enough to satisfy the superradiance condition. So the phase velocity of the axions in these blue regions is slow compared to the rotational angular velocity of the black hole. Once you start populating the axions into this cloud around the black hole loses a bunch of its angular momentum, and it stops on this line where it's basically co-rotating with the axion cloud. At that point, the superradiance shuts off because you're no longer able to extract its rotational energy, and you plateau here. You can get the number of axions that you end up with by just counting the total angular momentum of the black hole in units of h-bar. So each axion carries away 1 h-bar from the black hole, and once you get order 1 of all of the angular momentum of the black hole, then you stop. Over longer time scales, you can also start to populate different angular momentum states of the axion, which are localized further away from the black hole and are less efficient at carrying away its energy. So that was the story for spin zero particles, where it's easy to visualize what their bound states look like. We also studied what happens if you have a dark photon, in which case you have some spin degree of freedom. And in that case, I'm showing at the bottom what the solutions look like. And again, it's pretty intuitive. You have a spin 1 particle. So now instead of just the cloud of particles carrying the orbital angular momentum of the state, now each particle also has its spin angular momentum. And like in regular quantum mechanics, you can add them together to get different combinations. And in particular, you can have states where you have angular momentum, total angular momentum, J equals 1, but no orbital angular momentum, L equals 0. So you can have like a spherical s orbital, which still carries a non-trivial angular momentum. And this would rotate around the central black hole spin axis with a frequency of equal to the particle mass. So this solution is interesting, and we showed with May and Robert that this leads to qualitatively different rates of superradiance growth, because if you have a bound state, which is localized much closer to the black hole, which you can have for a spin 1 particle, as I just explained, then you can have parametrically faster growth because the dissipation is so much bigger. You have many more particles interacting with the horizon of the black hole for an s orbital than you do for a p orbital. And so that means that instead of spinning down the black hole in about a year, as you did for a spin 0 particle like an axion, now you can spin it down in just a couple of days for the same mass ultralight particle. So that's the story of black hole superradiance and how you can build up a huge number of ultralight bosons in bound states just by extracting the rotational energy of a black hole. And these bound states can carry a few percent of the mass of the black hole, and it's distributed over tens of black hole radii. So if you think about what that means, this has the density that's comparable to the density of a neutron star, but it's all it's all placed in these coherent states of very light new particles. So that's the black holes are providing us with these huge energy densities of particles that otherwise may not even be there in our universe. They may be the dark matter, they may not, but the black holes are sourcing these giant gravitational atoms of these particles that then we can go out and look for. So before I go on to the last part of my talk, where I tell you how some exciting ways that we can look for this, I just want to stop and see if anyone has questions about this process. And if you're asking questions on Zoom, I probably can't see your question. Yes.
Does the equilibrium number of particles in a bound state depend on the density of particles away from the black hole? So you have some background density of particles, and then I would think that for any given black hole out there, it has some number of bound state particles. And I would think that that also depends on the background density. Is that the right way to think about it?
Yeah, so the question was if the final density of particles around the black hole depends on the background density far away from the black hole. The answer is no. So the process just depends on the extraction of the energy of the black hole. So it has, although the initial condition of how many particles you start with may depend on the ambient density. But even if you start with 0 particles, classically, this is an exponential runaway process, right? It's a completely classical instability where you start populating the particles and then you get more and more. So you start, you get 10 particles and then you get 100 particles, and then it's proportional to the number of particles that are already in the state, and it runs away until you extract all of the available angular momentum. So I'm glad you asked, because that's a very important point. It's completely independent of the ambient energy density, and you can also see that these are such huge densities that whatever you're doing in the environment around the black hole, like, you don't really care. This is going to completely dominate all of the dynamics. Other questions? Okay. So, oh yes, please.
How do you think about the chance of it spinning faster than the atom?
Oh, that's a great question. I'll come back to that in a bit. So the question was, how likely is it to have these fast spinning black holes? Well, let me answer quickly. So we have measured some rapidly spinning black holes, both in binary systems where you have a star that's orbiting the black hole and you can observe the properties of the accretion disk to infer something about how fast the black hole is spinning. And also at LIGO, you're able to measure how fast, for example, the final black hole or the initial black holes are rotating. And so we've seen some black holes that are very quickly rotating. We've seen some black holes that are not at all quickly rotating, but the overall distribution is really not well understood. Yeah. So good. As I said, there's a huge density of ultralight particles. So think of like a neutron star of axions sitting around this black hole. And we're going to look at 3 ways that we can try to observe it. Luckily for us, this energy density is time varying. So remember, it had this phase velocity of axions going around the black hole, and a varying dense source will generally produce radiation. And there can be 3 types of radiation depending on the specifics of the model that we're going to look at. So the most general is gravitational radiation, where we don't have to assume anything about the couplings of these particles to the Standard Model. You can also produce axion waves, and then, well, at the end, we'll talk about producing electromagnetic radiation. So, as I said, if you have this background rotating source, if you imagine this as a classical current, if you haven't thought about generating gravitational waves, you can think about an oscillating current producing electromagnetic waves. Similarly, an oscillating energy density and pressure will produce gravitational radiation. So here is again a simulation by Will East, where you see the dark photon superradiance cloud emitting gravitational waves at frequency of twice the mass of the particle. And this is exactly the type of gravitational wave emission that you would expect for a pulsar. Well, not completely exactly, but leading order is what you would expect for just a rotating object that's emitting gravitational waves. And this is a very different signal if you've seen those famous LIGO chirp plots where you have frequency that's changing very quickly with time as two things merge. This is a much different signal. It's quieter, but it's much cleaner. So you have a axion cloud that has a steady signal at a constant frequency. So here I'm plotting the gravitational strain, which is how much distances between two free-falling masses will stretch and shrink over time. And it's a very monochromatic signal that can last thousands to billions of years, depending on the parameters of the axion particle. And this fits very well into search strategies that are already happening at LIGO and Virgo, where they look for rotating pulsars that are not perfectly symmetric, and they have a little bit of gravitational energy, gravitational wave energy that's being emitted over time. So we looked at some of these searches with postdoc Sylvia Zhu in Germany, who's doing some of these pulsar searches. And we tried to estimate, given the current LIGO data that's already on tape, how many of these black hole axion cloud signals would you expect to see? So here we're looking for a monochromatic wave that's at a frequency of twice the axion mass. So as a function of the axion mass on the x-axis, how many signals would you expect to see in the data just from the black holes that are in our galaxy? So as you can imagine, this depends a bit about the black holes that are in our galaxy. So here I'm showing how many events you would see for a flat spin distribution. So this goes back to your question, if black hole spins are equally distributed between 0 and 1, you'd be able to see as many as a few hundred to 1,000 signals from all the black holes that were ever born in the Milky Way. Of course, we don't know that that's the distribution. If there are no rapidly spinning black holes that are born, you would expect instead tens to hundreds of events. If for some reason most of the black holes in our galaxy have very low spins, you would still expect a few signals to be visible today, but it's kind of at the 1 to few level, so it's hard to place any interesting constraints. But as the detectors get more and more powerful and the searches get better and better, even the most pessimistic spin distribution will give you some signals that you expect to see. And there's a bit of sensitivity on what the black hole mass distribution is, right? You can have different stellar progenitors form different black hole masses. You expect some light ones, some heavy ones. This is not as sensitive because what you really need is some large rotation, but there's also some dependence on how many events you expect to see on the black hole mass distribution. Yes.
Like this is just LIGO sensitivity, like current LIGO sensitivity, or LIGO?
This, yeah. So the question is what this assumes about the LIGO sensitivity. So this analysis is done with actual LIGO Virgo data that's on tape from runs 1 and 2. Right now we're done with run 3. And this is specific to these types of signals. So this is like actually what you would, if these existed, you would have expected to see these in the data.
So I could read this as a constraint. Like you're saying that because I haven't seen,
Yes.
this is already telling me that there's not a boson.
Exactly. So the question is if you should read it as a constraint, and yes, you can read it as a constraint. The reason I'm not phrasing it as a constraint is precisely because of this point, which is that it depends on the distribution of the black holes in our galaxy, which we're slowly starting to learn more about with data from gravitational waves and also better observations of other stellar remnants like pulsars, where we can more directly measure their properties. But if you believe that black holes have a flat spin distribution between 0 and 1, then you can already exclude basically all of this axion parameter space. And this is a very exciting time because there's now tens of analyses happening for these types of processes with gravitational wave data. So we first proposed these back in 2015 and 2017 to look for these types of signals. And since then, there are people, both me and my collaborators who work on these pulsar searches with LIGO data, as well as the actual LIGO-Virgo collaboration, which recently put out these types of results. But I do want to give you the caveat that if you hear that there's an exclusion from LIGO for these particles, you should always ask, what are you assuming about black hole distributions? Because that's still quite a large uncertainty at this point. But it's very exciting because now there's all of these searches going on with different types of analyses and different assumptions. So we may soon discover a continuous wave coming from these gravitational atoms. So the next type of wave I want to tell you about is axion waves. So if you have, this is something you might be a bit less used to. If you have an oscillating axion field and it's self-interacting, it can source axion radiation. This is not something that happens with electromagnetic waves, because at least in the free theory, electromagnetic waves, in the linear theory, electromagnetic waves don't interact with themselves, but axions can source other axions, just like electromagnetic currents can source electromagnetic waves. And in particular, as I told you at the very beginning, the axiom potential is expected to have some nonlinearity. So the same potential that generates the axion mass also generates higher order terms like a quartic interaction. And with Marius, Olivier, and Robert here, we tried to understand what kind of consequences this would have on the evolution of these superradiant clouds, and if there were new observables that we could see. And the most exciting part is that if you have these axion interactions, then you can have new processes that are happening. So before I told you about how the black hole would, let's look at this plot here, which is the number of particles as a function of time. So before I was telling you about how superradiance takes the energy and angular momentum of the black hole and places it into a cloud of axion-like particles. And that's this blue line here that keeps growing exponentially. If you have self-interactions between the particles, then you can have new processes where you source axions from the axions that are already there. In particular, you can take two axions which have angular momentum 1 in this blue cloud and make one axion that has angular momentum 2 in this red cloud. And you have some extra energy that's left over in a fourth axion that falls back into the black hole. So it means that instead of the black hole just pumping this level, which is growing exponentially, now you have this new energy source that's building up this next level, which is much further from the black hole. Eventually, you start a new process where two axions from the red level, which have angular momentum 2, can drop back down into level 1 and fling one axion off to infinity. So now you have this constant cycle where the black hole is pumping axions into the cloud. They're mixing among themselves and sending axion waves to infinity. And that reaches some quasi-equilibrium configuration where you have constant energy emission, but now it's happening not in gravitational waves primarily, but in axion waves. And if you estimate how long the signal in axion waves can last, it can basically be as long as the age of the universe. So you have a constant source of axions that the black hole is producing that's then being emanated off to infinity. And in the interest of time, I won't go into the details, but basically we're already looking for axion waves. We're building detectors to look for axion dark matter. And some of these detectors, for example, the Casper wind detector, which looks for a particular interaction of axions with standard model particles, is particularly sensitive to these waves because they're traveling pretty fast. So alpha is this gravitational coupling constant. So typically the speed of these axion waves is still non-relativistic, but much faster than typical dark matter speeds, which gives a bigger signal in some types of detectors. And so this is an estimate for what kinds of signals you would expect. So on the x-axis is the mass of the axion-like particle, and on the y-axis is basically the size of the effect of the axion on nuclear spins. And here are some projection lines for different model and experiment assumptions. But what you should take away is that for open parameter space of axions, so things that are not currently constrained by any other experiment, these different black holes that are nearby, like Cygnus X1, give different phone numbers for these different black holes, which we have measured to be fastly rotating, could produce signals above sensitivity of some future dark matter detectors. So these detectors are already being built and developed, and you just need to do a different type of data analysis to look for these axion waves. Okay. So the takeaway here is that you have these huge numbers of axion-like particles, and depending on the parameters of the model, you can look for these in different ways. For very low self-interactions, you would be dominated by gravitational wave emission. For larger self-interactions, which is parameterized by this y-axis coupling, you would emit axion waves. And so you would be able to learn something about all of this open parameter space. Lastly, something that I'm very excited about is emission of electromagnetic radiation. And this happens not for axions, but for the dark photon cloud that I was telling you about. So if you have this dark photon cloud, basically the way you can think of it is that this here is like a dark electric field that's constantly rotating around the black hole. And this dark electric field can be very, very large, much, much larger than anything you would see in our universe. Now, if it doesn't couple to particles in the standard model, then the story goes through as before. You have gravitational wave emission, and you can look for it at LIGO. Some of the details are different than for the axions that I told you about. But if there's a coupling to the standard model, which at some level we expect to be there, then you can get very exciting dynamics. So you have this large electric field. If it has a small interaction with our particles, then it's going to start accelerating electrons along the direction of the electric field. But remember, this electric field is rotating, so eventually the electrons will curve and start to emit high energy radiation. That high energy radiation will scatter off of the already existing large electric field that's there. This is called assisted Schwinger pair production. So basically you have high energy photons as well as a large energy density of an electric field that can create electron-positron pairs. And now you get a new runaway process where you can get very quickly huge numbers of electron and positron pairs in the vicinity of the black hole. And this process is much, much faster than both the rotation frequency of the electric field as well as the overall growth of the cloud. So what happens is you get this dipole that's trying to track the electric field that's produced by the black hole, and rotating dipole will give you some sort of electromagnetic radiation. And this is basically going to give you some sort of deposition into electromagnetic fields that you can hope to observe. Now, just like, so this is, we're using similar types of analysis that you use for pulsar dynamics, where you have huge rotating electromagnetic energy densities, and you have emission radio waves and X-rays and gamma rays. This is work in progress. All we can see right now is that you get a lot of energy out. So let me give you some idea. So here on the x-axis is this alpha parameter, which you can think of as changing the mass of the black hole, for example, for a given particle mass. And the y-axis is the amount of luminosity we expect in these different types of components. One is coming from resistive losses in the cloud, and one is coming from dipole radiation, which then can also re-emit and rescatter. And this is in units of ergs per second, in case you're not thinking about luminosity in astrophysics every day. The total bolometric luminosity of the Crab pulsar is down here. So that means not just the visible radiation coming from the Crab pulsar, but the whole energy that's being emitted is roughly here. And our energy that's being emitted from these dark photon superradiance clouds is can be several orders of magnitude larger. So if you have a new black hole that's formed, it would be very exciting to look for a signal coming from it in some sort of periodic fashion. So this is the power on a sphere in theta 5 space that you expect to see. And you can see there's this periodic pattern that will rotate around at the frequency of the particle mass. And you expect to see these pulsating emissions in electromagnetic power and X-rays or gamma rays, maybe radio. Again, this is still something we're working on, but so take it with a grain of salt. But I think this is a very exciting signature of dark photons in this mass range that can give you basically a new type of pulsar in the sky instead of a neutron star with magnetic field rotating around it. Now you have a black hole with electric field rotating around it, and that can give you huge emissions. So I think I am out of time, so let me stop here. And I hope I've convinced you that black holes are excellent detectors of new particles, and they can open a new window on ultralight particles across the spectra, and we can hope to fill out the rest of the standard model with some axions and dark photons. So thank you. Questions?
More questions.
I have several questions, but I'm not a black hole expert, so one is in terms of the number of super-rotating black holes that we can detect or expect to detect, would you think that there would have been more super-rotating black holes that there are going to be more? We're not going to be here, but down the line, what more?
So the question was if you expect to see more quickly rotating black holes produced earlier in the age of the universe or later. That's a good question. So roughly, just in general, star formation was more active early on, so you expect more just total numbers of black holes. And also, I believe people think that the metallicity in the star can affect the final spin, and that might also reduce the rotation in later times because you have more sources of energy dissipation from the core out to outer layers of the star, and that would reduce the final rotation of the core that's going to form the black hole. But these are quite qualitative arguments. So roughly, it's order 1 decreasing over time, but yeah. Yeah.
Another way, is it the same to say that it's lossy if I can extract energy from it, or are they two different things? How do I think about that?
So the question is, in an analogy with the rotating cylinder, how do you talk about the black hole being lossy? And it's the actual horizon of the black hole is the lossy surface. It's a perfect absorber. So if you shoot waves at it, they'll get absorbed. Now, if you look at it from infinity, if the black hole is rotating quickly, that actually looks like the amplification of the number of particles far away from the black hole. Is it the same as frame dragging? I mean, it's related to frame dragging in that you have rotation. If you want to think about it in like black hole terms, you can think about the Penrose process where you can throw in some rock that splits and some part of it will carry away some more energy because it slows down the black hole rotation. So this is, if you want to think about it in that language, this is kind of the wave analog of that. Yeah. Good.
I think this might have been on slide in your last electromagnetic. You talked about what kind of couplings are being probed. Yeah, I think it was the one.
Oh,
yeah.
Yes.
The one basically. Yeah. So what kind of couplings do they probe? Like how strong?
Yeah. So this is So the question is how strong couplings can you probe, and you can. So what you need is that you want the accelerate. You want to start this process of string repair production. It's a runaway process. So you need to
because you were asleeping.
particles fast enough to radiate high enough energy photons to start that process in the time that it takes the electric field to rotate around. And that's roughly gives you epsilon of 10 to the minus 10, 10 to the minus 11, depending on the other parameters. And then if you're bigger than that, then you'll just start doing that before the cloud finishes growing, and then you'll keep pumping up this plasma as the cloud is growing. And then we haven't thought too hard what happens if epsilon is super large, but that's already excluded by other measurements. So this is the kind of exciting region here. It's a few orders of magnitude below what you can probe with the CMB.
Aren't able to do this repair production process, do you still have any interesting like heating of an accretion disk or something like this? If you're at say a larger black hole, like
Good. So yeah, what happens in between and what happens with accretion disks? I don't know. It's very complicated. So we think right now probably nothing super exciting happens. I mean, you accelerate particles, they radiate, but there's so much other mess that it's not observable. What happens in an accretion disk is an interesting question that we have not studied in detail yet because it completely changes the boundary conditions of what your electric field is doing. So the simplest problem that we're tackling first is just the isolated black hole in kind of a dilute plasma that feeds its own plasma cloud. But if you start already with some matter density around, then that might change the picture. And yeah, it'll be very interesting, but it's even more complicated. Yeah, in the back, Ani.
What prevents, I think you like you just said you have a magnetosphere in a black hole already. So what prevents you from, I mean, can you actually form large electric fields without screening, without any screen by the particles?
Yes, so that's the idea is exactly what's happening is that you are producing these charges which are trying to screen this electric field close to the black hole. They will be screening it, but now you have this dipole of charges that's rotating around and it's emitting some power. Now, of course, that power will get rescattered by all the plasma, and so it might not actually come out as like a coherent radio wave, but it will dump a lot of electromagnetic energy. Far away from the black hole, if you're trying to keep up with the velocity of the electric field, you have to start moving faster than the speed of light. So then you're actually not really able to spin efficiently. And then there's other production mechanisms. Basically, there'll be acceleration and things of particles in the electric field far away from the black hole, which will lead to other types of electromagnetic energy deposition.
Right, but so I guess if you kind of have, would this be a one-off thing where you have a large electric field and you produce, like if you produce a lot of particles through a cascade, and I mean this can be an exponential runaway process, and then you bring the electric field, would it reemerge or?
No, it would just keep rotating and radiating, and eventually you extract enough energy that you're done. Yeah.
Great, thanks.
Yeah. Was there another question over there? Or oh yeah, go ahead. Oh, good question. So there's a few. So yeah, how would you distinguish? You mean for the gravitational waves? So how would you distinguish between axion and a pulsar signal? So one is that pulsars are kind of evenly distributed in frequency. There's no reason why if we see one pulsar, the next pulsar we see should be very close to it in the rotation period. With axions, you really expect the frequency to be centered around twice the mass. So if there's just one new particle, then you'd expect to see all of the signals within a narrow frequency band. Let's see if I can show you a plot quickly, just so you can picture it in your head. So if you have a particle mass of, say, 4 times 10 to the minus 13 eV, you have, this is the frequency of all the signals you expect to see from the Milky Way, and this is the strain. So most of them will be clustered at twice the energy of the axion, which is slightly lower than twice the mass because you have some binding to the black hole. So the energy is slightly lower than just the rest mass energy. And that splitting depends on the black hole mass. So there'll be some spread. And there's also some spread because of Doppler shifting and things like that. But basically, it's very narrowly peaked. You can see this is, within less than a hertz in frequency. So if you see multiple signals and you see this kind of clustering, then it's a pretty telltale sign that there's some fundamental frequency that's at play here, which is not the case for pulsars. The second thing is you have, because of this energy, binding energy, as the cloud empties out because it's losing energy to gravitational waves, there's some self-energy of the cloud that's getting reduced. So there will actually be a small spin up because now the axions are having to climb out of a more shallow potential well than they did at the beginning, just because there's fewer other axions around. So now the energy is actually increasing, which is the opposite for what you expect for a pulsar. So the frequency of the gravitational wave would have a slight positive drift. This is pretty difficult to distinguish because it could also be, some relative motion of the star of the black hole relative to you, but it's a potential signal that it will be coming from this. Yeah. Yes.
You think about the differences that you would get if you take the two fields instead of the one.
Okay, what did we think about spin 2 fields? We thought briefly, so people have studied spin 2 field superradiance. When we thought about our self-interactions, we basically estimated what typical consistent models of massive spin 2 fields would give you. And typically those self-interactions are, typically the theory is not consistent at the field densities that you get. So basically, to me, it's not super interesting because your theory is breaking down far below the amplitudes that you reach when you get interesting phenomenology. But people have calculated like the rates and stuff, just as a general exercise.
But I kind of have a fun sort of science adjacent outreach question. How would you explain the research to a fifth grader?
To a fifth grader. Yes, I may have to get back to you on that, but we look for special new kinds of glowing objects in the sky that can tell us about new types of, well, I guess they don't know what a particle is, but new types of particles that we haven't discovered yet. Yeah, I'll have to think about it. Maybe that would differ. Yeah.
For the electromagnetic signal, would you look for the signal after merger, or you would try to detect, like, is that the kind of signature you're at?
Yeah, the question is for the electromagnetic signal, would you look after a merger or what? So yeah, so you do both. Look for after a merger and try to do a blind search. The signals will probably not last a super long time for the brightest signals, maybe tens of years is a typical time. The problem is that, so I did show the energy output, and it's pretty big, but it's not like extragalactic big. So depending on where we end up in this parameter space, most of the mergers that are happening right now are probably too dim to see, but it's still, since this is kind of an order of magnitude estimate right now, it's still worth doing kind of a search to see if there's something exciting happening. And you could also look for more closer by black holes. We expect many, many black holes that we haven't seen in the Milky Way. There was just one recently discovered through microlensing by Hubble, like a few kiloparsecs away. And now that there are more and more searches like that, we'll see more black holes, and we could try to point at those. Yeah. Yes. Yes.
So I had a very similar question. So, and then in your answer to another question. So,
Also, please feel free to leave this. I'm happy to stay and keep answering questions, but I realize it's getting late. Sorry, go ahead.
the time for ring up.
Yeah.
In one guy,
Yeah.
really short, right? That's on the order of days. Right?
Yeah, it depends on the parameters, but yeah.
And then you just said that the time that the actual signal will last is only order years.
Yeah.
So can there be many sources in the Milky Way that are local enough, that are bright enough to see, that we wouldn't separately see in LIGO? I mean, fast forward 10 years when we'll have been running LIGO for 10 years, right?
In LIGO, sorry, you mean in LIGO mergers?
Yeah. Because otherwise, how do you get a thing that's spinning so fast that hasn't long ago spun down?
Yeah, it depends. I mean, I just give like kind of order of magnitude example. So if you have a smaller electromagnetic coupling, or a smaller, like a more diffuse cloud, then all of these time scales are much longer. So then the question is, yeah, exactly, like, would you be able to still see them from inside the galaxy? And the hope is, yes, you would still be able to see some from inside the galaxy, but yeah. So for example, for the gravitational wave searches, you can have very bright, loud signals that you see from a merger that lasts for, say, days or months. Basically, the amount of power that you emit is always roughly the same, because you placed, the few percent of the black hole mass into this cloud, and now you're either depleting it very quickly in a bright signal or very slowly into a dim signal. So we're still trying to work out exactly like how many of these signals you would likely see with a random black hole distribution for the electromagnetic case, but you can expect to see some signals that last for a very long time, and they would just be a bit dimmer. Yeah. But yeah, that's the relevant question for observability.
It's kind of wild.
Okay.
I mean, the connection with the hydrogen atom is kind of interesting. And obviously, there's a lot of places where that analysis breaks down. In particular, repulsive forces of positive charges with other positive charges. I'm sitting here trying to imagine some case where you have an analogy of chemistry. Black hole has some sort of I mean, I know there are probably clusters of black holes that are not so close that they're violently approaching each other and then destroying each other. So is there any hope for some sort of black hole atom black hole down states that are purely like the electronic state of
That's a fun question. In principle, maybe there's actually a recent paper that claims that you could have something like this. Probably these are not very stable. I think the more fun part is if you have a black hole with a cloud around it and another black hole that's orbiting it, then you can have some really interesting dynamics where you have like excitations from one level to another because of the perturber of the external black hole. That's basically driving at some frequency, some transitions between levels. And this, some people have studied, and whether it's observable or not, whether you land in a frequency band that can be seen at LIGO or LISA, it's not super clear, but it is possible and can lead to interesting dynamics. But in principle, anything that's rotating, that has rotational energy and has some dissipation can do this. So composite system can also do this. The problem is it's not spinning very fast, and the absorption is also not very big. So probably you're not going to get anything super interesting or super stable. Yes. The status of superradiance around pulsars is complicated. So there have been a few attempts to look at what happens if you have axions or around pulsars that get either or scalar fields. So you need absorption. So just regular gravitational forces are not enough. In principle, you could have, gravitational excitation of the vibrational modes of a pulsar, and then they start emitting, and then that leads to losses, but that's very small. So you have to assume some new interactions, and if you assume those new interactions, like coupling to nuclei, then those are constrained by other things. So the signals are typically, the rates are typically very, very weak. You can also try to couple to like electromagnetic fields. But black holes are the best because they spin the fastest and have the biggest dissipation. Everything else might happen, but it's very messy and hard to, and usually gives small rates. But I don't think there's like a conclusive, all the estimates that are kind of rough have been, it's probably too slow. And so people haven't really taken the step to more realistic systems because of that. Yeah.
There are any more questions? I'll take it. Otherwise, we can maybe put aside.
Yeah, I'm here all week, so if you have more questions, please come by. I'm in variant 320. Thank you.